In much of mathematics, as soon as a certain process is mastered, the question then becomes, can this process be undone? And I think like there are two processes in algebra that really exemplify this idea. So, for example, like if I wrote down this product, x plus 4 times the quantity x minus 5, and I say expand this product, meaning go ahead and you might refer to it as foiling out. Well, if I say expand this, then that will produce this trinomial, x squared minus x minus 20, right? But then I could start with this trinomial. I could take the x squared minus x minus 20 and then say factor this. If I say factor this trinomial, then again, with whatever process you've learned for factoring, right, we would come up with the x plus 4 times the quantity x minus 5. So in some sense, you can say that expansion is like the inverse operation of factorization. In fact, we could set up a nice little, not really a flow chart, but in a sense, kind of a flow chart. If you, let's say I start with the quantity x plus 4, quantity x minus 5, and then down here, I'll have the trinomial x squared minus x minus 20, and then let's say on this side, I will have the expansion, or just say expand, and then going back this way, I would say factor, right? So in one nice little cycle or loop, right, we can show how these two operations essentially they cancel each other out. So if I expand and then factor, I'm going to end up with what I started with. If I started down here and then I factored and then expanded, then again I will end up with this. Much in the same, it's the same concept between addition and subtraction. They are kind of inverse operations. Multiplication and division, they are seen as inverse operations, and there are tons of them elsewhere. The square and the square root under certain assumptions, right? The e to the x and the natural log of x. Again, those are all inverse things, right? So you look at the title, and the title is antiderivative. Now, the prefix anti really is just saying that you're going to do kind of the opposite. You're going to undo what we did to find derivatives. So now we're going to kind of add to this collection of operations or pairs of operations that act as inverses of each other, right? So we're going to define the whole idea of what it means to undo a derivative, right? Because so far, the majority of our study has been to find the derivative of a function. Now, granted, beyond that, we've learned how to apply the derivative, but now we're just going to focus back on the operation itself, right? So let's start with a definition. So a function, and I'm going to call it big F, so uppercase F of x, is called an antiderivative, right, of a function, another function obviously, and this one's going to be denoted little f of x on some interval. I'm just going to call that interval I. So this big f of x is called an antiderivative of little f of x if what has to be true? Well, if I differentiate my big F and I get my little f, then we're going to use the word antiderivative to describe I guess the relationship between big F and little f, right? So that's the idea of a antiderivative. It's a function that when we differentiate it, we'll get the function that we're looking for, right? That which is denoted here little f of x, right? So here's just an example. So if I have a function like 1/3 x cubed, right? Well, when I differentiate this, and let's say I call that little f, well, using our power rule for derivatives, we will have 3 times 1/3 times x to the 3 minus 1, so we will end up getting x squared. So what we can say, in fact, let me go ahead and put a subscript here. So let's say f1 there, f1 there. There we go, right? So what we can say is this function f1 is an antiderivative of this function x squared. So therefore, we can say 1/3 x to the third power is an antiderivative of x squared. Now, the fact that we're using the word "an" as opposed to "the," it kind of implies that, man, maybe there are more than them. Maybe there's more than one antiderivative of x squared. And look, so for instance, if I did something like this, if I named a different function and I defined it this way, if I took the same 1/3 x cubed, but let's say I added 2 instead, so I added this as my constant. But then when I take my derivative of f2, right, and again, notice I'll still get the same little f of x. I'll still have my 3 times 1/3 times x to the 3 minus 1. Now the fact that I added this constant here doesn't change the end result, because I know when I differentiate my constant I'll get 0, so I still end up with my x squared. So we found another one, right? So what this implies, so therefore 1/3 x cubed plus 2 is, and let me say this, another antiderivative, right, of x squared. Put my periods there. And the thing is, it doesn't matter what constant I put here. Any constant, I could put 1,000, I could put pi, I could put 0.1, I could put the square root of 5. Any constant, any real number that I add on to my 1/3 x cubed. So it's almost like you can think of this as like your base or parent, antiderivative. And then if I add any constant to that parent or base antiderivative, it will still be an antiderivative, right? In fact, so we're going to say this. So in general, for any constant, so this is my notation for saying, so any constant that is an element of the set of real numbers, so any real number, right? If I do big F of x equals 1/3 x cubed plus that constant, right? This, right, function, right, is an antiderivative, right, of my x squared, right? Because in general, so what we're saying is, if I take the derivative of this, which is saying take the derivative of 1/3 x cubed plus c, then I will always, as long as c is a constant, right, I will always get x squared, right? So the whole idea of, so, like when we take a derivative, like the first derivative of a function, we're going to get a specific function. However, when we take or find an antiderivative of a function, we're not just going to get one, but we're actually going to get infinitely many. And there's a really cool way of interpreting this plus c. There's a really nice geometric way, which we'll talk about in a not so distant video, right? So let's go ahead and give some more terminology, right? So the process of finding antiderivatives, and I'll make it a plural since now there for each function there will be many. So the process of finding antiderivatives, that process is called antidifferentiation. It doesn't have to be hyphenated. I'm just kind of doing that for dramatic purposes. So either antidifferentiation, or they're sometimes referred to as integration. So both of these mean the same thing. It means find all the antiderivatives of a particular function, right? And now, so what we would like to be able to do, just like, and I used it up here, just like how we have these two nice notations for a derivative. We have a prime notation, we have the Leibniz notation, the dx notation for finding a derivative. We would want something similar, right, for finding an antiderivative, so that we don't have to keep writing the phrase antiderivative or or integral, right, which is another word that we will use a lot of going forward. But we need to come up with a nice notation for this, right? So the following anti-differentiation notation, right, is used. So if I have a function, and again I'm going to call it little f of x now. So if I want to indicate that I'm finding the antiderivative of this function, I am going to use this notation. So there's kind of this, what we call either an antiderivative sign, or sometimes it's called an integral sign, and then you put your function there whose antiderivative you're trying to find, and we put a dx there, right? We need this, right? Because essentially, since the differentiation is done with respect to x, you would expect that the anti-differentiation would also be done with respect to x. So whatever your independent variable is, its differential is added at this point, right? And again, it might seem a little, I don't know, superficial to be putting this dx here, but again, in the not so distant future, you're going to see a very significant role that this dx plays, right? So again, this is what we're going to use to indicate finding an antiderivative. And then over here, we would write down what that antiderivative is. So what I'll just say, using the same notation that I did earlier in our definition, I'm going to put the big F of x there, and then we will put this plus c, right? So let me just kind of give some terminology that's associated with everything that I've written down here, right? So again, this is kind of it's sometimes called the integral, and that's coming from the integration verb, right? But so this is kind of the integral sign. The function here that you are trying to find its antiderivatives, this function here is often called the integrand, right? And then the dx here, I remember we studied differentials, and this is the differential of x. In general, it will be the differential of the independent variable, but I'll write that this is the differential of x. And then this, obviously, over here, this would be, again, I'll just say an antiderivative, right? So it's one of them. And then the plus c that we add on, so this plus c is called the constant of integration. And this constant plays an important role in lots of uses of antiderivatives, right? So it's not something that you can just forget. Even though you might say, oh, the constant doesn't really matter because when I differentiate it, it goes to zero. That's true. But going in the opposite direction now, where essentially we gain a constant, it's important that we indicate that that constant is there. All right. So, earlier I gave you like this little flow chart that kind of, again, summarized the relationship between expansion and factorization. Well, we can do the same now, right? We can do the same for differentiation and anti-differentiation. So I'm going to do it like this. So I have my big f of x plus c, and then I have my little f of x there, and then I can do my loop. So to go from this to this, right, this is our process of differentiation. So we can do that. And then going in the opposite direction now, this is again our new focus, that of anti-differentiation, right? And again, it's not a problem that I didn't do my hyphen there. Again, it doesn't have to be hyphenated, but now we can say, okay, these are the two processes, right, that really embody all of the calculus that you study, and typically your first year of calculus will entail using derivatives and antiderivatives, right? So this gives us a nice relationship, right? Now, so okay, so this is kind of everything so far has been highly conceptual. I mean, I did one specific example with 1/3 x cubed, but think about all the functions that we know how to find the antiderivative of, right? So that we know how to find the derivative of. So every derivative that we know how to find can be expressed in terms of an antiderivative, right? Because they're essentially one and the same, right? So by that I mean, let me just do a few more examples, right? So we're going to do some examples, and through these examples, what I will do is try to kind of develop some of the general basic rules for anti-differentiation. Just like how we have some nice basic rules for differentiation, we have some nice rules for anti-differentiation. So we'll start with some specifics and then just make it a little bit more general, and that will wrap up this video. So for instance, let's say I know that the derivative of e to the 2x, right? So think of our exponential function, and we have to use our chain rule. So if we differentiate this function, then this will give me 2e to the 2x, right? Now, that also, this can be rewritten in different ways. And again, I'll do a couple little tricks here. Not really tricks, but just do some algebra with this equation, and then put it in a slightly different form, and then write down the antiderivative equation. Now, since this 2 is multiplying the e to the 2x on the right-hand side, I can actually divide both sides by 2, right? So I could do this. I could say 1/2 times the derivative of e to the 2x would be e to the 2x, right? So that's true. I just divided both sides by 2. And remember, we have the constant multiple rule for derivatives, which means usually when we apply the constant multiple rule, we take constants outside of the derivative. But it can work the opposite way as well. It's like we're trying to undo everything that we've done before. So what I can do is I can distribute the 1/2 and say that this left-hand side is the derivative of 1/2 e to the 2x. And then over here, I'll still have my e to the 2x, right? And this makes sense. We can see that this is true, right? If we differentiate 1/2 e to the 2x, I'm going to get e to the 2x. But now let me write down the antiderivative form of this equation. So think about it. If I differentiate 1/2 e to the 2x, I am going to get e to the 2x. That means the antiderivative of e to the 2x, right? So this is like now my little f, right? And inside the square brackets is my big F. So the antiderivative of e to the 2x dx is equal to 1/2 e to the 2x plus c, right? So these two are saying the exact same thing, but just in a different way, right? Again, it's the same kind of relationship between expanding and factoring. Over here now, it's differentiating versus anti-differentiating. Now, so the fact that I have a 2 as a coefficient here in front of the x, right, in the exponent, that's not significant. I could have a 5 here, I could have a 0.5, I could have a -10, I could have any constant there. So here is my kind of general rule, right? So in general, let me write this in a different color. So in general, again, this is just one example, right? I'm going to take a general rule from derivatives and come up quite easily with a general rule for antiderivatives. For let's use a. So for a, that can be any real number, let's say a not equal to 0, right? So I don't want to have a 0 in front of the x in the exponent. So if this is true, then I know the derivative of 1 over a, and this is another reason why I don't want a to be 0, because I want to set up this same kind of 1 over 2 fraction here, but now I'm going to make it more general. So the derivative of 1 over a e to the ax, well, that's going to be e to the ax, which then implies that the antiderivative of e to the ax dx is equal to 1 over a e to the ax plus c. Right? So you can say that this is one of our first rules of anti-differentiation, and this is a rule that we will use quite a bit. And all of these that I'm boxing off are these rules that you want to commit to memory or to understand that they exist and know when to use them, right? I mean, yes, there is some element of memorization there because you even have to remember, right? You have to remember, okay, that this rule exists and therefore I can use it, right? Now let's do something similar for the power rule. So again, I will do a general, a specific power rule example and then do the general case, right? So let's say we had the derivative of something like x to the 4th power, right? So then this would be, we know using our power rule for derivatives, it's going to be 4x cubed, all right? But then again, let's do the same thing that I did over here. Let's just try to get the function of x by itself and this constant that's multiplying it. Let's try to get it on this side, right? Let's try to get it on this side. So if I divide both sides by 4, so I'll have 1/4 times the derivative, this is a product there, of x to the 4th. That's equal to x cubed. And then you use our same constant multiple rule for derivatives. Bring the 1/4 inside the derivative. So we have the derivative of 1/4 times x to the 4th. Well, that's equal to x cubed. And again, that makes sense. We can use our constant multiple and power rule here and come up with this. So again, this implies, now let's write it with our new notation, the antiderivative of x cubed with respect to x. Well, that will be, again, my 1/4 x to the 4th plus c. So when you look at this, it's like, okay, well, what is the pattern? Like, what is the actual pattern here? And so so now let's see if we can do this in general, right? So in general, let's say for n, again, any real number, right? It technically could be 0, and this one could be 0, and you'll see why in a second. But let's say we have this, and I'm going to do something a little strange. What I'm going to do is I'm going to say, let's take a look at the derivative of 1 over, in fact, actually, let me say that here, n can't be -1, and you'll see why. Because what I'm going to do is I'm going to put n plus 1 in the denominator here. So if n plus 1 is in the denominator, then I can't allow n to be equal to -1. So I have 1 over n plus 1. This is still just a constant. And then I'm going to have times x to the n plus 1. And if I say, well, what is the derivative of this? Well, if I bring down this power and multiply this constant, I'll have n plus 1 over n plus 1, which is 1. So the constant would simplify to 1. And then I would have to subtract 1 from this exponent, which just leaves x to the n. Right? So this is kind of a general way of kind of doing what I did right here. Right? Notice this has the same specific form. This is that same kind of general form. Right? But then what this means now is this. So then I can write down the antiderivative version of this rule. So this is saying the antiderivative of x to the n with respect to x, or dx, that's equal to this expression. So it's 1 over n plus 1 times x to the n plus 1. Then I have to do my plus c, but then I have to put this to say that I can only use this rule when n is not equal to -1. So then this is for n not equal to -1. And this, let me box this off, this is our power rule for antiderivatives. And look at what it does. It says whatever this power is, add 1 to that power, and then divide by the new power. Let me make that n more clearly. Right, there we go. Right. So then the question is, what happens when n is equal to -1? Well, let's see. So if n is equal to -1, we would have to find a function. So let's ask this question. So what happens when n is equal to -1? So if I have to find the antiderivative of x to the -1, right, I can't use this rule anymore because then it breaks, right, because I would have that 0 in the denominator. But then I have to ask myself, can I think of a function that when I differentiate it will give me 1 over x, right? And with a little bit of thought, you would come up with the natural log function. So we end up having the natural log of x plus c, right? Now, going back to derivatives, when we did the derivative of the natural log function, we showed that even if there are absolute values, right, around the x, we would still end up with the derivative of 1 over x. So alternatively, so there are some instances where we want to use this function as the antiderivative, right, of 1 over x. So I'll go ahead and It kind of box this off because this is kind of a special case for the power rule for antiderivatives, right? I think I want to do one more of these, because so the ones that I'm doing now, these are like the extremely basic ones that you just immediately you want to get accustomed to it. Let's do one of our trig functions. I'm going to choose the cosine, or let's do the sine function, right? So let's do a specific case. So let's say we have the derivative of the sine of, and I'm going to put a there as well, right? Something like this. So again, a is some, oh, that doesn't look very pretty, does it? So let's say a is a real number. So I'm just going to go straight to the general form now that we hopefully have gotten used to the idea. So I am going to apply the chain rule here, and then that will give me a cosine of ax, right? So then let's do the same trick. Again, if I assume that a is not equal to 0, I'm going to divide both sides by a. So I have this. Right, so we have that, and then I will have the cosine of ax there, and then do that same thing, bring the 1 over a inside, so d dx, 1 over a sine of ax, and then here I'll have the cosine of ax. So now let's write this, right? Let's write this in the antiderivative form. So what this implies is that the antiderivative, again, here's my little f of cosine of ax dx is equal to 1 over a times the sine of ax plus c, right? And this one I'll box off, and there we go. So then here we have another rule, right? And again, I could go through the process, and I'll just say, and here is the version for sine. So and the antiderivative of the sine of ax dx is now we remember when you differentiate cosine, you get negative sine. So if you want to get a positive sine function, then you'd have to differentiate a negative cosine function. So then we have a negative 1 over a, and then this will be cosine of ax plus c, right? So what I wanted to do with these kind of 4 rules is just to show you, right, that essentially the process of anti-differentiation it's almost like educated, I don't want to say guesswork, but it kind of is guesswork, but it's based on what we know about derivatives. So if you have a solid foundation in the rules of differentiation, we can take each of these rules, like this one, right, like this one right here, and reformulate it in such a way that we come up with a rule, an equivalent rule for anti-differentiation, right? Now, going forward, the process of anti-differentiation or integration, it can get tricky, right? Because not every rule will be able to just do a nice reversal like I did here. But this is the foundation. This is the start that we need to build upon, right? Now, there are other ones that we could reverse. We could do this for tangent and all these other ones. And as we go into it and start actually solving particular problems, then we will encounter these other rules. But again, these are rules, as I said, and I'll say it one more time, that are based on what we know about derivatives. So if you can find a derivative, you can express that same derivative in terms of the antiderivative notation. All right, so next up in our next video, we're going to be looking at some properties of antiderivatives, and then start actually going through and not just coming up with these rules, but actually using them in specific examples. So I'll see you then.